Okay, in the previous class we have seen how we have designed the binary parallel adder, and also we have seen the adder subtractor circuit, and in this class we are going to see actually how we are going to design a 4-bit CLA. And we have also seen actually how the carry is looking ahead. Carry gets generated for the next bit operation. Okay, so that's why the speed of the operation is very fast in this CLA, and how the design is, I'm just going to explain it now to you. So as I told you, the complete CLA is going to be done with the help of two equations. One is S3, which is sorry SI, which is nothing else my PI XOR CI, and CI plus 1 is GI plus PI CI. So this is the basic equation for designing the CLA. Okay, do you all understand? So now the thing is here, what we need to do in this case, so there will be 4 levels always to design the CLS. So please see here what I am doing. So this is my A0, B0. In order to design the first bit, actually A0, B0. Okay. So this generates me P0. Okay. Next, this is A0, B0, and this gives me G0. Okay. Next, how to get this sum? I am going to get the sum which is S0, which is P0 XOR C0. Do you all understand? So C0 is what? So this is my P0 and this is my C0. I'm getting the sum for this 0th bit. I'm getting the sum P0 XOR C0. So this is my XOR operation, so that I got here S0. And what is my C1? I have got C1 as G0, P0, C0. Okay. So see here, my G0 is ready over here. If I perform P0, C0 operation, so this is my P0, C0 here, and this is my G0. G0, P0, C0 gives me, after OR operation, it gives me C1. Okay. So this is the thing. Now this C1 is the next bit operation required for the next bit operation. So see here, what is my next bit for the one first, for the next bit, what is my S1 is P1 XOR C1. So P1 will be what? P1 is nothing else my A1 B1, which is nothing else my P1. So this is my A1 B1, and you can see here what is someone is P1 XOR C1. So C1 is available here. If I can take P1 to there, so I can tell that this is my S1. So you can see here, for someone C1 is already ready for 0th operation. During 0th operation itself, I have obtained this C1, and this C1 I have been using for next bit operation of sum. Are you understanding? Now tell me, what is my C2 next bit C2, which is C1 plus 1 is nothing else my G1 plus P1 C1. As we know that G1, which is C2, which is G1, P1 C1 means P1 multiply G0 plus P0 C0. So which is nothing else G1 P1 G0 P1 P0 C0. Do you all understand? This is my C2. Okay, so how to get this? So you can see here G2 is nothing else P1 G0. So this is my P1. What is G1? G1 is nothing else A1 and B1, which gives me here G1. Now you can see my C2 next bit carry C2, which is G1 plus P1 G0 P1 P0 C0. So where I will get all this? So 1 minute, I'll just make it in the zoom out version. Okay, so please see here G1 P1 G0. So P1 G0 is where? So this is my G0, and this is my P1 P1 G0. Okay, P1 P0 C0. So where is my C0? So this is my P1 P0 C0. So this is my P1 P0 is here, You can say, you can also take it from here, P0. Next, C0. C0 is from here. So this is the way you can take P1, P0, C0, and from here G1. So this all you can take and make the OR operation to get this C2. So this is your P1 G0. This is your P1 P0 C0. This is your G1, which gives you C2. So for the second bit operation, which is A1 B1, this is second bit operation. For second bit operation, I have next bit ready carry. Okay, which actually requires for the next bit operation, which is S2, which is nothing else P2 XOR C2. So which requires for the next bit. But when the carry gets generated, in the previous bit operation itself, carry gets generated. That's why carry look ahead error it is. Okay. Next C3. C3 is nothing else my G2 P2 C2. I have been G2 plus P2 C2 means here P2 C2 is nothing else my this one G1 P1 G0 P1 P0 C0. Okay, so you can get it from G2 P2 G1 plus P2 P1 G0 P2 P1 P0 C0. So this is my C3. So next bit carry is getting generated. For this second bit I'm getting my next bit carry C3. Okay, like this way you just has to do. Okay, so all the 4 bits. Okay, this is very important, students. Little bit clumsy circuit you need to do proper way. So what you need to do here, you need to get here A2 B2. Okay, and this is your P2 and this is your G2. Okay, from this you can come to know that you require actually what P2 XOR C2 is your sum 2. So P2 XOR C2, where is C2? Here it is C2. P2 XOR C2 will gives you sum 2. Okay, but for C2, C3 you would have this much of expression. So it require how many? 3 AND gates and 1 OR gate, 4 input OR gate. So you need 3 AND gates and 1 OR gate to design to get the C3. So C3 is ready now before going for the operation of third bit. Are you understand? That's why carry is ahead here. Carry is ahead here. You have to perform this, students. I'm not doing. So now one important concept I'm going to tell you. Now tell me in carry look ahead adder, how many labels are there? The labels are actually, this is one label. You can say this completely one label. So label 1 consisting of what actually? Label 1 consisting of one XOR gate and an AND gate. Okay, one XOR and one AND. Okay, next what is label 2? Label 2 is all these AND gates are label 2. All these AND gates. Okay, all these AND gates are my label 2. Label 2 are all AND gates. Okay, now what are OR gates? These all OR gates, sorry, label 3. These all OR gates are my label 3. So label 3 is my all OR gates. Okay, and label 3, level 4 is of what? All this sum we are getting na XOR. All these XORs are my level 4. Level 4 is all XOR gates. So what do you understand from this? A carry look ahead adder requires how many labels mainly? Level 1, level 2, level 3, level 4. So there is 4 labels it requires. So what are those labels for carry look adder? Any bit carry look ahead adder, it requires these many 4 labels. What are those? XOR and in level 2 it require AND gate, level 3 it require OR gate, level 4 XOR gate. Do you understand or any doubt, students? Please let me know. Now the question is, so which adder circuit is we have to adopt? Okay, so who is faster? Either BPA is faster or CLA is faster. I'm going to tell you. Okay, so before going to tell that, one important concept I'm going to explain you, that is called propagation delay. Okay, propagation delay, which is also called tau PD. So very important 2 mark question, students. What do you mean by propagation delay? I'm just explaining a little bit easier way to you. Please try to understand what is propagation delay. Before I'm going to what I need to conclude, I need to conclude here which is faster. Who is faster? If tau PD of BPA is less or tau PD of CLA is less. If anybody is higher, that I can say that that is little bit slower speed. Okay, so we'll see those things. I'll at the end we'll comment it. Don't worry. So what do you mean by propagation delay? Mainly the propagation delay is nothing else. Propagation delay. Please see here. This is a NOT gate. Am I correct? If I'll give A, I'm getting output A bar. Okay. So now tell me what is propagation delay? Propagation delay is always inside the gate. What is that? If I'm giving here T, I can give here either 0 or 1. Am I correct? At T equal to 0 second, I gave here, let's say 0. At what, after what time it responds at give me 1. That is called propagation delay. Let's say it took 2 nanoseconds to provide me output. Let's say it take 4 nanoseconds to provide me output. Understand? So I'm giving here 0 at t equal to 0 second, but I am getting output after 2 nanosecond 1. Okay, initially it is 0 here up to this. After 2 nanosecond I am getting 1. Are you understanding? So 2 nanosecond is the propagation delay of this particular gate. Are you understanding, students? What do you mean by propagation delay? After what time this gate responds to my inputs? Okay, at sorry, I made it wrong. After what time I am getting my output to that particular input? It's called propagation delay. Okay, do you all understand? Now similarly, we can always remember propagation delays are produced from the gates. So here, how many gates I have been required actually for my CLA? I just require for level 1 XOR and AND. For level 2, I need AND gates. For level 3, I need OR gates. For level 4, I need XOR gates. Okay. So I have been requiring here many gates actually to design the CLA. So now tell me, so 10-bit CLA. So for 10-bit CLA also, tell me how many levels will come up, students? Only 4 levels. Why? Because if the bits are increasing, it will increase this only. This way only it will increase. Am I correct? It will increase this way only. Just bits will be increased like this. Okay. It's not increasing this way. Okay. Always all XOR and AND in the level 1. AND gates are in the level 2. OR gates are in level 3. XOR gates at the end are in level 4. So do you all understand? So a CLA, it may be a 10-bit, maybe a 20-bit, it may be a 100-bit CLA also. It has 4 level of design. Am I correct? Now tell me how to calculate this propagation delay. So you understand here how to calculate the propagation delay. In order to find out the propagation delay, try to understand in the level 1, it has many XOR gates and AND gates. Am I correct? It has 4-bit CLA, let's say. How many AND gates and XOR gates in level 1? In 4-bit CLA, level 1 has how many XOR and AND gate? XOR are 4 and AND gates are 4. Am I correct? For 4-bit CLA in level 1, I am saying. Okay, level 2, level 3, I have not yet discussed. For level 1, it has 4 XOR gates and 4 AND gates. Now tell me what would be the propagation delay of this? The propagation delay of this is what? So whichever is giving maximum propagation delay, that we have to take for the level 1. Let's say this XOR gate is giving propagation delay 3 nanosecond, AND gate is 6 nanosecond, this is 8 nanosecond, this is 2 nanosecond. Okay, let's say this is 3 nanosecond, this is let's say 8 nanosecond, 4 nanosecond and 12 nanosecond here. Now tell me what would be the propagation delay of the level 1? Tau PD is what? Which gate is giving maximum propagation delay? That you have to take. So 12 nanosecond is the maximum propagation delay. So tau PD of level 1 is 12 nanosecond. Understand? Similarly, all these AND gates you have to take and find out tau PD of level 2. What is the maximum? Okay. Do you all understand, students? What is level 1 propagation delay? You have to take the maximum propagation delay among all the gates of level 1, that you have to take here. Similarly, maximum propagation delay of among all the gates of level 2, maximum propagation delay among all the gates of all the OR gates of level 3, maximum propagation delay of all the XOR gates of level 4. All these you have to calculate, then add it up everything to get the final propagation delay of 10 bit CLA or 4 bit CLA. Everything is set. Understand, friends, or any doubt? Let's say we'll do one problem here so that you will have better idea actually. Those problem actually came in 2018. Very important question. Please try to understand. Then after that we can point out which adder circuit is a better one. Okay. So here the question is, what is the propagation delay? What is the propagation delay of 20 bit CLA if XOR gate has 6 nanosecond delay and AND gate has 4 nanosecond delay, OR gate has 3 nanosecond delay. Okay. So now you have to calculate. This is very important 2-mark question. Okay. Sometimes some 5-mark question also maybe come up. So you need to know what is asking actually in the question. The question is actually you need to find out the propagation delay. Tau PD you need to find out. Okay. Of 20 bit CLA. So here the question is you need to find out the propagation delay of 20 bit CLA. Okay, first of all, you need to know what is the requirement for CLA. CLA has 4 levels. What are those levels? Level 1, level 2, level 3, level 4. Okay, 4 levels. So what are those 4 levels? In it may be 20 bit CLA, it may be 10 bit CLA, it may be 4 bit CLA. It has 4 levels. Okay, level 1 has XOR and level 2 has AND, level 3 has OR, level 4 has XOR. Okay, any doubt on this? So now tell me, what is the question given here? Question is given here, if XOR gate has 6 nanosecond delay, so XOR gate has 6 nanosecond and AND gate has 4 nanosecond. Okay, AND gate has 4 nanosecond. I'm just writing. OR gate has 3 nanosecond. XOR gate has 6 nanosecond. Understand, students? So now tell me what would be the propagation delay. You have to find out the maximum propagation delay among these two. What is the maximum? 6 nanosecond is the maximum. So here in level 1, propagation delay is 6 nanosecond, plus level 2, 4 nanosecond, plus level 3, 3 nanosecond, plus level 4, 6 nanosecond. So what will be the delay, tau PD? The delay of 20 bit CLA is 6 plus 6, 12, 4, 16, 3, 19 nanosecond. Okay, students, do you all understand how to find out? Very simple. Okay, so here you need to find out each level propagation delay. At the end, you need to add it up to get the final propagation delay of that 20 bit CLA. So it is 20 bit CLA, it is 100 bit CLA, it is whatever may be bit CLA. Now in the question, let's say the question has been given instead of 20 bit, 1000 bit CLA. So what would be the propagation delay, student? Same. Are you understanding? For 20 bit CLA, 1000 bit CLA, every time the propagation delay is 19 nanosecond only, because the levels are getting fixed here, 4 levels. Okay, that is the reason. Now, the same question we are going to do. What is the question actually here? Please try to understand. Find out the propagation delay of, let's see the question, another question. So these are all very important, students, not in the book actually. Please try to understand. Find out the propagation delay of 20 bit binary parallel adder, 20 bit binary parallel adder, same as above. Means what? XOR gate has 6 nanosecond delay, AND gate has 4 nanosecond delay, OR gate has 3 nanosecond delay. Okay, with this particular propagation delays of the gates, you need to find out the propagation delay of 20-bit binary parallel adder now. Okay. So what you need to do here, you need to find out here one important concept, tau PD of 20-bit binary parallel adder. Okay, that you need to find out. Now tell me, for the 20-bit BPA, how many full adders required? 20 full adders required, or else one half adder and 19 full adders required. Let's say I am going to take these 20 full adders now. Okay, let's say I am going to take this 20 full adders I just require for this 20-bit BPA. Now tell me, so here for 20-bit BPA, I just need how much? This, let's say FH0, this is carry bit 0, which is 0, A0, B0, and this is my sum 0. Like this, I would have 20 full adders. Am I correct, students? Like this, it has 20 full adders. Am I correct? This carry is propagating like this. This is M1, A1, B1. Okay. Now tell me, if I can calculate this FA0's propagation delay, how much? Then can I multiply this with 20 with one full adder's propagation delay? Obviously, yes, because these are all these many labels. Are you understanding? Okay. So if I can find out the propagation delay of one full adder, I can easily multiply with 20, then I can find out that. Now tell me, in full adder, how many XOR gates and AND gates required? I just require like this. This is my full adder. Am I correct? So this is my full adder. Are you understanding, students? Very important question I am explaining here. This is my order. So now tell me, AI, BI, CI, this is my SI, this is my C0. Okay, output carry. Now tell me how many labels are here. In this full adder, how many labels? Label 1, next label 2, next label 3. So in label 1, it has XOR and AND. In label 2, again, it has same XOR and AND. In label 3, it has OR gate. So a full adder must have how many labels? Label 1, label 2, label 3. Okay. Now tell me, what would be my full adders, one full adders propagation delay? Tau PD, how many? You have to find out what is XOR gates. XOR gates is 6 nanosecond, AND gates is 4 nanosecond given. XOR gate is 6 nanosecond, 4 nanosecond, OR gate is 3 nanosecond. Am I correct, students? Yeah, correct. So, what is the propagation delay of level 1 of full adder? You have to choose the maximum, which is 6 nanosecond, plus propagation delay of this maximum 6 nanosecond, plus propagation delay maximum 3 nanosecond. So, how much you got here? 15 nanosecond you have got here for propagation delay of one full adder. But I need to find out propagation delay of 20-bit BPA. In order to find out 20-bit BPA, I just require 20 into propagation delay of one full adder. Am I correct, students? So which is nothing else, 20 into one propagation delay of full adder, how much? 15 nanosecond. How much we have got here? 300 nanoseconds. So what is propagation delay of 20-bit BPA? It is 300 nanoseconds. So what do you understand from this? Can you comment it over here? So I have got for 20-bit CLA 90 nanosecond, and for propagation delay of 20-bit BPA 300 nanosecond. Which is faster? You can tell me now. So if in the question it is asked, always propagation delay of 20-bit CLA is much lower than 20-bit BPA. Propagation delay of 20-bit BPA. So this CLA is operation, much faster operation compared to other adders. Any doubts, friends, on this? Please let me know. Any doubt? Anil, D. Anil, are you there? Any doubt, Anil? Anil, are you there or not, Anil? Can you make you out from the room? Anil, are you there? Devatta Anil. Okay, you are out from the room. Okay. Now, Mansa, are you there? P. Manasa. Mansa, are you there? Bindu? B. Bindu, are you there? Hello? B. Bindu.
Yes, sir.
Okay. Did you understand how I have find out the propagation delay?
Yes, sir.
Okay. If there is no doubt, we'll proceed further. So next part of our syllabus is actually one more very important concept, BCD adder. Okay, very important for main exam point of view. BCD adder, 14 mark question or 7 mark questions now is the trend actually. It will come. So please try to understand this. What is BCD adder? So BCD adder is actually comes under BCD arithmetic. Okay, BCD arithmetic. Okay, next BCD addition, we have to follow certain rules. Some rules you have to follow. What are those rules? I'll tell you, don't worry. So first, what are the rules here? In order to add two BCD numbers, we have to follow certain rules. What are those? Mainly, first of all, we have to add the corresponding digits of each BCD number. We have to add the corresponding digits of each BCD number. Okay, I'll tell you this, don't worry. Next, after that, after adding, what you need to do after adding, we have to carefully check the result. We have to see the result carefully. Okay, result carefully. If result is if result is greater than 9, greater than 9, or any carry arises, or any carry arises, okay, then result is said to be invalid, said to be invalid BCD number. Okay, do you all understand this? What you need to do here, first of all, you have to follow certain rule while adding two BCD numbers. In order to add BCD numbers, okay, we have to add the corresponding digits of each BCD numbers. After adding, we have to check the result. If the result is greater than 9, or any carry output, then the result is a invalid BCD. So we need certain correction here. What is the correction? I will tell you. In order to make invalid BCD to valid BCD, we need certain correction. What is the correction? The correction is here. We have to add we have to add 6. 6 means 0 1 1 0. We have to add 6 to the invalid BCD, to make it valid, to make it valid. Do you all understand, students, or any doubt? Please let me know. So what you have to do, first of all, in order to add two BCD numbers, we have to follow certain rules. We have to add the corresponding digits of the BCDs. After adding, we have to see the result. If the result arises greater than 9, or any carry arises, then the result is said to be invalid BCD. In order to, we have to make some correction there. What the correction is? In order to make it valid BCD, we have to add 6 to the invalid BCD number to make it valid. Now the question is how we have to do that. I will give you one example so that you can understand over here much better way. So see here, let's say I am going to add here 8 with BCD number 4. Okay, so this is BCD 8 with BCD 4. These are the 2 numbers. Okay, now what I'm going to tell you, in order to add these two BCD numbers, I have to follow certain rule. First rule is it should be added corresponding bits, BCD numbers. So first of all, tell me here, 8 is what? how to represent 8 in BCD number? I can represent it in 8421 weight. Okay, this is the BCD weight. Actually, I have already told you each corresponding decimal numbers can be represented as 4 bits with 8421 weights. So now 8 can be represented as 1000. Similarly, 4 can be represented as 0100. Now I have to add these two. Okay. So do you all understand? So what is this I am doing here? First of all, in order to add two BCD numbers, I have to follow certain rule. We have to add corresponding digits. So this is and this is corresponding digit 0 plus 0, 0, 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1. Now you have to see the result carefully. What the result you got here, students? 1100. If you add this 1100, what is this? 8 plus 4, 12. So result is 12. Am I correct? Now tell me, 12 is greater than 9? Yes. So we can say that whatever result we have got, it's a invalid BCD. Okay. So we need certain correction. What is the correction? I am going to tell you. So I have told we have to add 6 to it. 0, 1, 1, 0. Do you all understand? To make it valid BCD, we have to correct. Why? Because I have got your result 1100, which is 12, which is greater than 9. It is a invalid BCD. We need certain correction. What is the correction? The correction is to add 6. So I have add here correction 6. So after that, what I have got here? Again, you have to add this 0 plus 0, 0, 0 plus 1, 1, 1 plus 1, 0 with carry 1, 1 plus 0 plus 1, 1 with carry, sorry, 1 plus 1, 0 with carry out to the next bit, which is 1. So here what we have got, as I told you, each BCD bits are for 4 bits. So here 4 bits, remaining 4 bits will be here. You can append 3 zeros over here. So now what you got from here? You have got here 0010. If you take 8421 coding, this is 2 and this is 1. So we have got here 12. Okay, 1 2 BCD 1 2 12. Okay, so what is the BCD addition result? Somebody will ask you, what is the BCD addition result? BCD addition result is what? 10010. Now somebody will ask you, what is the binary addition result here? If you have done it addition using binary, what would be the result, friends? 1100. So do you all understand the difference between these two? So BCD addition means you need to check whether you are getting a valid BCD or not. If it is invalid BCD, you have to correct it by adding plus 6. After that, you need to have groupings of 4 bits and write down the result as a BCD addition. Now I will do one more question here so that you will have more idea. So let's say 9 plus 5, BCD 9, BCD 5. Sorry, first of all, you have to tell me these are BCD numbers. So what is my corresponding bits here? 8421. 9 means 1001. Okay. Now 5 means what? 0101. Now I need to add corresponding bits. 1 plus 1, 0. Okay. Next 1 plus 0 plus 0, 1, 1, 1. Now tell me 1110. How much is 8 for 12 plus 13? I have got here 13. 13 means greater than 9. So it's a invalid BCD. In order to make it valid, I have to add 6 to it. Plus 6 I have done because I have got the invalid BCD. Okay. So in order to make it valid, I have just add 6. That's 000. 1 plus 1, 0. 1 plus 1 plus 1, 1. 1 plus 1, 0, 1. So what I have got here? I have got here, this is 4 bits and this I have gone appended to get remaining 4 bits. I have got 1, 4, 14. Okay, 14. So this is the addition. So do you all understand what I am doing here? Mainly I am designing here in such a way that I am going to have, if any invalid BCD, I have to add 6 to it to get it valid. Okay, this is called the BCD addition. Any doubt, students? Do you all understand the formula and rule?
Sir,
Yeah, please tell me.
sir, why you are added again one and one at
What I
last?
have added 1 1 1?
At last.
Where? Where I have added? Hmm?
Here again you have added one one.
Here,
Yes, yes, sir.
because carry, I got 1 plus 1 what?
Okay, okay,
0 with carry 1. Then 1 plus 1 plus 1, 1
okay.
with carry 1. 1 plus 1, 0 with carry 1. Then I take this carry. Understand? This is a
Yes, sir.
normal addition formula, nothing else. If you add 1 plus 1, it gives you sum 0, carry will be go to the next bit. Carry will go to the next bit. 1 plus 1, sum 1, carry 1. Okay, like this way. Do you all understand? So very simple. So this is called BCD addition. Now, in the exam, this may ask as a 2 mark, but mainly what it will ask to design. So how the question will come? Design a BCD adder circuit. Okay, so which may be a 7 mark question, very very important. Okay, which may be a BCD adder circuit. Design a BCD adder circuit. Okay, please see here what we can do. So first of all, tell me, BCD adder is a combinational circuit, okay, which performs the procedure of BCD addition. So BCD adder circuit is nothing else. It's a combinational logic circuit, okay, which performs the procedure of BCD addition. Understand, students? Very simple. So now tell me one important concept. What is the procedure of BCD addition? The procedure is this one. Am I correct? Corresponding bits it will add if any carry generated or result is greater than 9, needs some correction to make the invalid BCD to valid BCD. So this is the procedure. Am I correct? So BCD adder circuit is a combinational logic circuit which performs the procedure of BCD addition. So procedure you know that. What is the procedure? If carry is generated or sum exceeds 9, if carry is generated, okay, and generated or the sum is exceeded by 9, exceeded 9, we need correction. We need correction. So what is the correction here? The correction would be by adding 6. Adding 6. So this is the procedure. Am I correct? So I have to design a circuit in such a way that. So now tell me what we are doing mainly here. We are adding two 4-bit numbers. So can I say that a normal adder circuit can do this? Okay, it actually do. A 4-bit adder circuit can perform this particular addition operation or not? Yes, a 4-bit adder can do this. Okay, so we know that there is a IC called 74LS283 IC, which is a 4-bit adder IC. So I can take a 4-bit adder IC and and perform the addition operation whatever the sum comes here, S0, S1, S2, S3. Now I am going to check here if the result is greater than 9 or any carry is generated here or not. Okay, are you all understanding? Then after that I need to add with 6. So if any carry generated, I need again a 4-bit adder circuit here. Am I correct? Which adds fixed 6 with variable result of invalid BCD. Are you understanding, students? So how many 4-bit adder circuits I require actually? I require actually two adder circuits here. Okay, where the first adder circuit will performs the addition operation. Please try to understand. So it's very important question. So it actually performs 74LS283 IC, which is a 4-bit adder IC, which performs the addition operation between four bits of A and 4 bits of B. And this is my carry input also it has. Okay, if carry input is not there, you just need to give 0. Else, so here which is nothing else, A4, A3, A2, A1, B4, B3, B2, B1. Okay, and it provides a carry, may provide a carry, but four results will come. What are those results? S4, S3, S2, S1. Now the thing is here, the sum whichever comes over here, it is going to be checked either it is greater than 9 or any carry arises. If carry arises, it may be 0 or 1. If carry arises means obviously it is 1 only. Am I correct, friends? Obviously it is 1. If these, for these two purposeful cases, I would have another adder circuit required here. Am I correct? But for that, before going to that, I need to discuss one important concept here to fill up this circuit. Okay, so I would have truth table of the BCD adder. So what would be the truth table? We are going to see. Either I will get here from 0000 to 1111. Am I correct? These many 16 combinations of sum may come. Am I correct, students? So if for those particular combinations of sum, what I have to do correction, I am going to do here. Okay, so when I need correction, actually I need correction after 9 up to 9 0000 1001. I don't need any correction because all these are less than 9. Now after 9 means here, starting from 10 onwards, 10 onwards means I would be having 1010 1011. From 10 onwards up to 1111, the probable outputs which are greater than 9 required correction. Required correction means the output for this error circuit, these are erroneous circuit, so I need correction, means output will be 1. For this no error, output is 0. Understand, students? Now I have to develop this truth table first. So see here how I am developing this truth table. So I may get some S4, S3, S2, S1, and whether I need a correction or not, who will tell? The output, error output will tell whether I need a correction or not. So here this sum is a 4-bit sum which is starting, this is MSB, this is my LSB, from 0000 0001 0010 0011. Okay, please try to understand, students. Very important concept I am explaining here. And here next 0100 0101 0110 0111. Okay, next to 1000. Okay, 1001 1010 1011. Okay, next 1100 1101 1110 111. Okay, so these are the certain 16 cases can be possible in this sum. Okay, in this sum I would be expecting 16 cases. Okay, so those 16 cases when I need correction up to 0 1 2 3 4 5 6 7 8 9, up to 9 I don't need any error. This is not having erroneous output, so I don't need any correction, so I'm just putting here 0. There is no error. But after 9, from 10 onwards, it is having error, so I need to have correct it. So I am just putting here, these are all erroneous outputs, means invalid BCDs. From 10 to 15, min term 10 to min term 15 are having error, and it's a invalid BCDs, and it requires certain correction. So what is the correction? I'm going to tell you. Okay, how the correction I'm going to tell you. Don't worry. So for that, in order to design this erroneous circuit, what I need to do? Along with this, I have to design this erroneous circuit. If this erroneous circuit gives the result 1, I need to add the result with another 0110. So now, so what is this? I need to have logic expression. I need to find out for error circuit. Okay. So what is this logic expression? Very simple. It is actually 4 variable. So I have just taken here 4 variable KMF. Very simple. Please try to understand. Very important concepts I am explaining here. So these are my S4, S3, S2, S1. So this is my S2 bar, S1 bar, S2 bar, S1, S2, S1, S2, S1 bar, S4 bar, S3 bar, S4 bar, S3, S4, S3, S4, S3 bar. Okay. Now we know the minterm position from M0 to M9. So these are all zeros, no error. But M10 to M15, it has error, needs some correction. So now grouping, how the grouping is, this is one of the grouping and this is another grouping. So what I got here, S4, S3, what I got here from this, S4, S2. So error circuit Y S4, S3, S4, S2. So this is my error circuit output. So what I need to do here, please try to understand. I'm just designing the circuit here. So that you can understand very well. So how the design it, please if you are not understanding, let me know. Okay, now I have told you for any BCD number, you need to have a 4-bit adder which adds 4 bits. So what is the adder circuit here? Requires 7 for LS. I'm just designing the logic now. Final logic design I'm doing. Okay. 4-bit adder circuit. It takes the inputs 4-bit A and 4-bit B. Okay. A4, A3, A2, A1, B4, B3, B2, B1. Okay. 74LS283 is the IC and it generates a 4-bit sum. Okay, what are those? S4, S3, S2, S1. Okay, so these are the adders, and along with that, it may generate some carry. Okay, now if what is the error will come? The error is S4, S3, S4, S2. So see here how I am designing S4, S3. Okay, please try to understand very important concept. S4, S3, S4, S2. Okay, if this is 1, please try to understand. If this is 1, this is y. If this is 1, what I need to do, students? I have to add this sum, whatever I have got here, this sum. Just has to extend it. It's very important. This sum 74LS283. This is S4, S3, S2, S1. This sum, it requires some correction. So what is that correction? It need to be add with fixed 0110. Am I correct, students? It need to be fixed 0110. So now see the circuit how I am doing. This ground, 1. Okay, if this is having error, then 1 will come over here and it will sit over here as a 1 1. Otherwise it is always 0. Always it is 0. Okay, so if it is not having error, means less than, this sum is less than 9, means 10008. 8 means less than 9. So what will happen here? This will perform S4, S3, 0, and this is also 100. 00 means sum is 0. If there is no error, always it is 0000. It is going to add with 000. Finally we can get the output here. Okay, finally we can get the output over here. But if it is having error like 1100, it comes. Now see here what I am going to do. If it came 1100, 1100 means what? It's a 12. 12 means obviously greater than 9. Needs some correction. It result will go over here 1100. Am I correct? Because directly it's connected. Okay. Now 1 and 1. What is that? 1. Okay. And 1 and 0. What is that? 0. 1 and 0 OR operation. What you have to do? 1 and 0 OR operation means I have to get 1. So 1 means here all these will be okay. Are you understanding? This 1 and 1 will come. Y equal to 1 means it is connected, so on. Now it will add with 1100 with 0100, which is 6. Okay, are you all understanding? Now this is a invalid BCD number. Make it valid by adding 6 to it. Okay, so this is one of the condition. If my result comes greater than 9, now the thing is, if there is a carry, what will happen? If there is a carry, so I'll just modify the circuit like this. So if carry gets generated, but result is not having any less than 9. So 0100, another case I am taking here, students. Please try to understand. Okay. So let's say it is not, it is 0100, which is less than 0100 means what? 0100 means it is 4, but there is a carry. Okay, 4, but there is a carry. So 4 is less than 9. So 0100 directly come over here. 0100 will directly come over here because it doesn't need any correction. But since a carry is generated, this carry will go over here. Okay, it is 1. So 1, and this is 010 or operation is 1. Again it will make this as a 1 1. So we need second correction, which is plus 6. Do you all understand that there are two cases I have explained? One is greater than 9 and one is having carry. So if there is carry, also we need correction. So y equal to 1, so it become 1 1. So it's going to add with the result 0110 to get the final sum. Okay, so this is, here we'll get actual BCD addition result. Any doubts, students? Please let me know. So this is the circuit. Any doubt, please let me know. This is very important, students. If you have doubt, I will explain it again. Please let me know. Very important. Really, it will come in the exam, main exam. Surely it's coming every time. BCD Adder circuit. Any doubt, please let me know. Pardu, did you understand Pardu? Pardu, are you there? Pardu, are you there? Vivek, yes. Did you understand, Vivek?
Sir, once you repeat.
Hmm? Once you want me to repeat, where you did not get, please let me know. So, did you understand up to this? What is BCD addition? First of all, did you understand? 1, let's say 8 plus 4. I'm just doing this 1000. 4 is 0100. So, in order to add this, what I have to do? Corresponding digits I need to add. This performs by the help of 74LS 283 IC, which performs this, and it will gives me the result S4, S3, S2, S1. What it will give? 0 plus 0, 0, 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1. So it is greater than 9 now. Now I have got here 1100. Okay. So I have got here what actually? I'm just doing this. Yes.
Sir, am I
Any doubt?
audible, sir?
Yeah. Who is this?
Sir, Parthu, sir. I am
Okay.
Parthu.
Okay. No problem. 1000. I'm adding with 4. 0,
Mic
1,
was
0.
not working, sir, then.
Not an issue. Now you understand or not? Tell me. Is it okay to you?
Yes, sir.
Okay, so I'm just doing this example 8 plus 4. So I got here 1100. So, and carry is 0. Here I got carry 0. Okay, because I have not got carry here. Okay, are you understanding? So now tell me S4, S3. If I end operation, what I will get over here? S4, S3. I have got over here 1. Okay, and this carry is 0, so 0 will come over here, and S4, S2, what I will get? 1 and 0 is 0. So 0 1 0, if I perform OR operation, what I will get here? 1. Okay, so we need correction here because it has error, and what correction it need to do? Plus 6, 0 1 1 0. So I'm just going to add here plus 0 1 1 0. Okay, which gives me 0 0 1 1 1 1 0 carry 1 1 0 1 0 with carry 1. So this carry will come over here. Now 0 0 1 0, whatever carry gets generated will be generated from here as a carry output. So here what I will get actually result? I will get here result 0 0 1 0 with carry output 1. Okay, so this is actual BCD addition. So what do you got from here? 1 and this is 2. 12 we have got as a result. Any doubt? Whoever asked me doubt, did you understand, student? Any doubt
Yes,
on
sir.
this now? Yes, yes. Any doubt, please come up. Any doubt? Whoever asked me, did you got it?
Yes, sir.
Okay. Himabindu, did you understand? Okay, Himabindu.
Yes, sir, I understood.
Okay, so these are mainly our adder circuits. So we have finished many things today, like adder circuit, adder subtractor circuit, then BCD adder circuit, then carry look ahead adder circuit, then what is propagation delay, which adder is better. Everything we have discussed. Please prepare properly, students. If there is any doubt, you can ask me. You can ping me in my WhatsApp. Not an issue. Okay. So